On va laisser la parole à Steve Awodey, qui est de la Carnegie Mellon University à Pittsburgh, et qui est spécialiste, enfin ses domaines de recherche, ses thèmes de réflexion sont en histoire de la logique, de la philosophie analytique, la philosophie des mathématiques, la logique, et même la théorie des catégories. Donc pour une conférence intitulée MacLean and Carnap's Logical Syntax of Language.
Okay, thank you. It sounded about right, as far as I can tell. So it was okay. I too would like to thank the organizers, and especially Michael Wright. And you'll excuse me if I'll repeat that when he comes in the room. So I think this will be the first talk of the conference that does not mention cohomology. But that's okay. I guess the idea of the conference is in part to recover some of the earliest origins of category theory, also from other points of view, including the logical point of view. And my paper will try to highlight some of Saunders Mac-Lane's contributions to modern logic, its mathematical development, philosophy, and advancement. I'm going to especially focus on one particular episode involving the logician and philosopher Rudolf Carnap, and the surrounding circumstances and ramifications of this interaction between Mac-Lane and Carnap. It's partly because I think it's a relatively interesting episode. It's fairly unknown, but also it serves as a convenient vehicle for the story that I'm telling. Please don't get the impression that I consider Carnap's importance as an influence on Mac-Lane to be as great as the amount of time devoted to Carnap in this talk suggests. The paper has 6 sections. I'll begin in section 1 with a brief review of Carnap's work, leading up to his opus magnum, The Logical Syntax of Language, published in 1934. The Syntax was probably the most important book, or one of the most important books, in mid-century analytic philosophy. So I'm talking about, just to briefly recap, I'm talking about the relationship between the early Saunders Mac-Lane, and also later then, and Rudolf Carnap, the author of The Logical Syntax of Language. So this will be some background to Carnap's project of the logical syntax, in particular some of the philosophical motivation for the logical syntax of language. Part 1 of 6. Rudolf Carnap's logical syntax. Carnap's project to construct a comprehensive symbolic language of science occupied his attention from about 1930 to 1950 and was centered on his search for a satisfactory definition of logical truth, or as he sometimes termed it, analyticity. The need for such a definition grew out of the program that he first conceived in early 1931, in which he dropped Wittgenstein's Tractatus conception of meaning and instead turned to a metalinguistic conception influenced by the methods of Hilbert, Tarski, and his student at the time, Kurt Gödel. The idea was to extend the meta-mathematical method beyond just the language of mathematics to the scientific language as a whole, in order to have a precise tool for a new kind of philosophical meta-science. The need for a definition of analyticity in this context grew out of Gödel's incompleteness theorem, which had just shown in the previous few years that there were apparently true sentences of arithmetic that were not logically provable, even given the axioms of arithmetic. Up until then, the obvious criterion of logical and mathematical truth for everyone had always been provability. Gödel had shown that this identification was unfounded and that logical and mathematical truth could not simply be assumed to be provability in a fixed system. The result had not only threatened the logicist thesis of the logical character of all of mathematics, moreover, it called into question the fundamental tenet of Carnap's logical empiricism, according to which the only non-empirical knowledge is of the analytic kind, which is ultimately trivial and obtains in virtue of the rules of language. This was Wittgenstein's celebrated conception of the tautological character of logic, extended now, using Frege-Russell logicism, to the entire language of science. It formed the very cornerstone of the Vienna Circle's new logical brand of empiricism. So, through this novel combination of two recent scientific advances, on the one hand, Wittgenstein's discovery of the conception of tautology as the grounds for logical truth, and on the other hand, the Frege-Russell reduction of all of mathematics to logic, the empiricists of the Vienna Circle had solved, or thought they had solved, the traditional problem of the status of mathematics within an empiricist philosophy in a way that had not previously even been conceivable. So, if Carnap was to salvage this program, his new syntax method needed to provide a criterion for logical and mathematical truth that was stronger than provability in order to preserve the logical empiricism in the face of Gödel's incompleteness result. That's the motivation for the logical syntax. To accomplish this, then, the syntax program of Carnap had not only dropped Wittgenstein's conception of meaning, it had gone to the other extreme and dropped all talk of meaning whatsoever. The philosophical meta-language was restricted to statements about the formal syntactic structure of the scientific language. It could say nothing about what was out there, outside of language. The restriction to the formal, what Carnap called the formal mode of speech, was supposed to be observed in formulating all concepts pertaining to the logic of science, such as the concept of analyticity. One virtue of this procedure was that it ensured that any properties or results concerning the language of science that were arrived at with its help would necessarily be strictly formal and automatically devoid of any empirical content. So the syntax program provided a method for distinguishing the purely formal characteristics of a language from the descriptive facts expressed in the language, and ensured that logic and mathematics were empirically empty. Languages, according to Carnap, were constituted by rules, rules of formation for the expressions, rules of combination or transformation. The purpose of a criterion of analyticity was to specify the conditions under which an assertion in the scientific object language holds solely in virtue of those stated rules. In ordinary language, then, whether it is logically true. To see what sort of thing he was looking for, an analogy will help. So we're trying to understand how you could have a criterion of logical truth which is purely formal, based only on the syntax of the language, but is more comprehensive, stronger than simple deduction from the rules. So the analogy that I have in mind, in order to make this clear, is Hermann Weyl's analogy of a game of chess with the logical deductions. I think some of you, probably most of you, are familiar with this idea. Let us think of the rules of the game of chess as analogous to the rules of inference for a deductive system. The starting position of the pieces on the board corresponds to the axioms of the logical system. A particular position of checkmate represents a theorem which is true in virtue of the rules of the logical system. Now let's extend Hermann Weyl's analogy by the following idea. There are particular configurations of the pieces on the board which constitute checkmate, but cannot be arrived at by any sequence of permitted rules from the starting position. This is the way in which you could have a notion of analyticity which is strictly formal and yet more comprehensive than deducibility from the rules of inference. Carnap's first attempt to discover such a formal criterion of analyticity was stated in the first draft of the logical syntax of language. He wanted to arrive at the correct definition of analyticity for the scientific language he was proposing. This definition turned out to be defective, as Gödel pointed out to him in a letter in the autumn of 1932, and it's an interesting defect of Carnap's first proposal, but I don't have the time to go into it here. In essence, it amounted to the fact, which Carnap had not recognized, but Gödel had recognized, that truth can only be defined in a meta-language that contains the object language and goes beyond it. That is, has more expressive resources. This would become known to the world a few years later as Tarski's theorem on the indefinability of truth, with which you're familiar, I suppose. So Carnap went back to work and he came up with a new definition of analyticity using a stronger meta-language. He soon realized, however, that this new definition was somewhat arbitrary since it depended on a particular choice of the meta-language which was not distinguished in any way. Thus, it was not really what he had been looking for previously. It was not the definition of analyticity. It was a definition among many related possibilities. None of these, it seemed, was uniquely correct or canonical or privileged. There might be a natural one from some point of view, like third-order logic being used to formulate the definition for second-order logic, but this was far from being correct in the way that he had once sought. Having realized this, Carnap made his second big break with the Vienna Circles past. In early 1931, he had broken with Wittgenstein's conception of meaning. Now, in late 1932, he broke with the idea of correctness and of a single correct scientific language altogether. He adopted a thoroughgoing language pluralism and stated his celebrated principle of tolerance, according to which the language of science was freely choosable. The only arbiter was the purpose at hand and the practical usefulness of the proposal. Philosophical considerations about which language might be correct for some reason were to be replaced with the laying down of precise rules and definitions whose practical consequences could then be compared. With this shift, the position of analyticity within the overall theory also changed fundamentally. Before 1931 and 32, analyticity had resulted from the way that representation in language works. It had been a fact about the nature of language, according to Wittgenstein. The correct definition of analyticity had been something to be discovered. Now that there was no longer a correct definition, the concept of analyticity became something to be specified. What had previously been facts about the nature of representation and meaning in language now became constraints on the choice or the design of a scientific language. Logical truth thus became a matter of convention, to be decided on grounds of utility and purpose. According to the famous principle of tolerance, and now quoting from Carnap's Logical Syntax of Language, we do not want to impose restrictions, but to state conventions. In logic, there are no morals. Everyone can construct his logic, i.e., his language form, however he wants. If he wants to discuss it with us, though, he will have to make precise how he wants to set things up. He has to give syntactic rules rather than philosophical considerations. So much for the background to the logical syntax. Section 2 now, young MacLean as a logician. Saunders MacLean is known today as a distinguished algebraist and co-inventor of category theory. But when the logical syntax appeared in 1934, MacLean was just returning to the US from his studies in David Hilbert's Göttingen, which at the time was a world center of mathematics. MacLean had taken his doctorate under Hermann Weyl and Paul Bernays with a thesis in logic, which was somewhat unusual at the time, the only other logic student there having been Gerhard Gentzen. In fact, MacLean had originally gone to Göttingen in 1931 with the specific intent of studying logic. After taking an interest in it as an undergraduate at Yale through the impressive achievement of Principia Mathematica, the way that all logicians of the day became interested in logic, and through the later reading and studying of Hausdorff's Mengenlehre in his first year of graduate studies in Chicago. Finding no chance to study logic in Chicago, however, he decided to go to Göttingen in order to study it in the Hilbert School. Once in Göttingen, MacLean was at first disappointed to find that Hilbert himself had retired, but he soon found more than enough stimulation in the lectures of Weyl and Noether, and in his conversations on logic with Bernays during the breaks between those lectures. When he told Weyl that he wanted to write his thesis in logic, he was instructed to consult with Bernays, who in turn declined his first thesis proposals. At one point, MacLean wrote to his mother that he was so frustrated with the, quote, utter lack of philosophic grasp of the local professors toward my thesis, unquote, that he was, quote, prepared to transfer to the University of Vienna, where there are many who think as I do, unquote. But after a successful meeting with Bernays, in which he told him of the philosophic aim of the thesis, he finally persuaded him that it would be appropriate as a dissertation. Now, had he actually gone to Vienna at the time, 1933, the logician there would have been Gödel, not Carnap, since Carnap was already in Prague at the time. I don't know what MacLean, but MacLean didn't know this. He thought that it was Carnap, and that's why he wanted to go to Vienna, just at the time that Carnap was finishing the logical syntax. I don't know what MacLean knew of Carnap's work at the time, or from what source he knew it. Perhaps he was familiar with the textbook, Abriss der Logistik, which had been published in 1929. But his specific mention of many who think as I do, and his own philosophic aims, certainly also suggests at least some familiarity with and affinity for the Vienna Circle movement. The only evidence of his philosophic aims in the actual dissertation, which was entitled Abbreviated Proofs in Logical Calculus and was a brief exercise in proof theory, is in the very concluding section where he briefly discusses the notion of what he calls a leading idea, a leitende Idee. This is his term for something like an overarching conception which is at once both precise and general, and which, he says, should serve as the basis for the determination of the particulars, not only of proofs, but, as he says, of all mathematical processes, such as theories and mathematical operations. This conception, he says, and I have written out the quote just so you can study it a little bit. Is that okay? Yeah, that's pretty good. Yes. Good. This conception, he says, suggests a vast and important field of study for mathematical logic, the study of the structure of the elements of mathematics and the determination of this structure through leading ideas, which, now recall, are not simply proof-theoretic leading ideas. Moreover, such an investigation, he says, should strengthen the connection between mathematical logic and mathematics. For a successful consideration of the structure of mathematics must obviously begin with mathematics itself. From this point of view, mathematical logic should not become a separate and highly specialized field in itself. I think it hardly requires pointing out that these remarks could now easily be taken as applying to category theory. The dissertation itself was undistinguished, even by MacLean's own admission. It had been completed in a great rush after Hitler's rise to power and during the disintegration of the German university, as Jews were dismissed from their posts and many of their colleagues either resigned in protest or fled in caution. Bernays, who was Jewish, was dismissed in 1933 before MacLean was finished. MacLean switched advisors to Weil. Although the thesis was read and approved by both men, it was Weil who examined him and is listed on the thesis as the referee. And MacLean credits, in fact, this conception of leading ideas to Weil in the thesis. Upon returning from Göttingen in 1934, MacLean soon landed teaching posts at Yale and then at Harvard, where he was strongly encouraged to leave logic behind and instead pursue the modern German style of algebra that he had learned in Chicago. This he did with great success. Nonetheless, he maintained an active interest in logic from then on. At Harvard, he was friendly with both Kleene and Rosser. He was one of the founding members of the ASL, Association for Symbolic Logic, and is so listed in the first volume of the Journal of Symbolic Logic in 1936, and he wrote several reviews of important works in logic at the time. One such was among the very first reviews of Carnap's Logical Syntax of Language, which in 1937 had just been translated into English. Section 3, Analyticity in Carnap's Logical Syntax. MacLean's review of the logical syntax, which he gave me a copy of and urged me to study when he learned of my interest in Carnap, was written for the Bulletin of the American Mathematical Society and published in 1938. It's quite detailed and overall positive, praising Carnap's main thesis regarding the importance of the use of logic in philosophy, and the precision and ingenuity of his many constructions, and the clarity of his discussions, in particular of Gödel incompleteness and the theory of types. But after a careful discussion of many preliminaries, finally the bomb drops, as MacLean observes that there is a fundamental flaw in the all-important general definition of analyticity in Part 4 on general syntax. To explain MacLean's objection, let's observe that in the logical syntax, Carnap had essentially defined logical truth, and I'm simplifying a great deal now, for the language of arithmetic recursively by putting, here's just a little slide there, by defining, so we're trying to define analyticity for formulas of arithmetic, and we simply do it recursively in the expected way here, where the brackets indicate interpretations of the basic terms. From a modern perspective, this is essentially the same procedure as Tarski's definition of truth in a fixed interpretation. What made it also suitable as a definition of logical truth is that in this particular case that Carnap was looking at, we're only dealing with arithmetical terms, numerical constants and predicates, and crucially, the theory of arithmetic is categorical. So any model of the axioms is isomorphic to a canonical one, the natural numbers. So it turns out that a sentence P of arithmetic is true in an arbitrary given interpretation, just if it's true in all the interpretations because of categoricity. And so logical truth is determined by considering just one model. You don't have to look at all the different models because they're all isomorphic. This special case was Carnap's starting point and his paradigm in his later semantic investigations, and this is rather unfortunate since the special nature of arithmetic results in features that are not typical of logical languages in general. Specifically, the above sort of recursive definition can also be used to define semantic truth in an interpretation for more general languages, but not logical truth in general. Thus, for languages that may also include non-logical terms, it becomes essential for Carnap to somehow distinguish the logical from the non-logical or descriptive sentences. Then, according to Carnap's approach, the logical truths will be those sentences that are both logical and are true in virtue of his general recursive definition of truth. So that's the procedure. We want to identify the logical symbols in the language somehow, and then we say the logical truths are those sentences which are true and consist only of logical symbols. It's not the modern way of doing things. Yeah? Now, since those logical sentences in general should be determinate, either true or their negations are true, without regard to the interpretation of any non-logical terms, Carnap has the ingenious idea of using determinacy to characterize the individual logical symbols themselves, and then letting the logical sentences be those consisting entirely of such symbols. Thus he writes, and now I'm quoting, "If a material interpretation is given for a language S, then the symbols, expressions, and sentences of S may be divided into logical and descriptive, those which have a purely logical or mathematical meaning, and those which designate something extra-logical, such as empirical objects and so forth. This classification is not only inexact, but also non-formal, and thus not applicable in syntax. But if we reflect that all the connections between logical mathematical terms are independent of extra-linguistic factors, and that they must be solely and completely determined by the transformation rules of the language, we find the formally expressible, distinguishing peculiarity of logical symbols and expressions to consist in the fact that each sentence constructed solely from them is determinate. Roughly speaking, then, the idea is to define the logical symbols of the language to be the largest collection of symbols, such that every sentence constructed only from them is determinate, just on the basis of the transformation rules of the language. This is the central definition that MacLean shows is mathematically unworkable. Mathematically, the problem is simply that there is no unique such maximal set of symbols. While there are various different sets, each of which are maximal in the sense that they admit no further extension, the intersection of all such sets, as Carnap proposes, is itself no longer maximal. The situation is quite similar to one arising frequently in algebra, as MacLean surely recognized. It's just like taking the intersection of all the maximal ideals in a ring or all of the ultrafilters in a Boolean algebra. The result is no longer maximal. In his review, MacLean gives examples of sentences constructed only from apparently logical symbols that nonetheless fail to be logical according to Carnap's defective definition. And he shows in particular that the existential quantifier there is does not satisfy Carnap's condition for being a logical symbol. He then concludes, now quoting from MacLean's review, such technical points might raise doubts as to the philosophical thesis Carnap wishes to establish here, that in any language whatsoever, one can find a uniquely defined logical part of the language, and that logic and science can be clearly distinguished. This point, of course, would later be the nub of Willard Quine's famous critique of Carnap's analytic-synthetic distinction, though Quine never acknowledged MacLean's priority, nor is it generally recognized even today. Indeed, the issue of precisely distinguishing the so-called analytic from the non-analytic or synthetic sentences has turned out to be one of the central problems of analytic philosophy, and the one that Quine made his reputation on. Let's recall Quine's criticism in a bit more detail. In his famous paper, Two Dogmas of Empiricism from 1950, he argues that the distinction between analytic truth, representing logic and mathematics, and synthetic truth, representing empirical science, cannot be rigorously made using the various procedures proposed by Carnap. And he concludes, quoting now from Quine, for all its a priori reasonableness, the boundary between analytic and synthetic statements simply has not been drawn. That there is such a boundary to be drawn at all is an unempirical dogma of empiricists, a metaphysical article of faith, end quote. Quine's language is more colorful, to be sure, but the point is exactly the same as MacLean's from 12 years earlier. Carnap has not succeeded in distinguishing the analytic statements from those whose truth is not determined by logic alone. An interesting point of difference here is that in MacLean's case, the criticism is based on mathematics. The proposed characterization in the logical syntax is mathematically defective. In response, as we shall see next, Carnap developed a new approach to analyticity based instead on semantics. In this later treatment, relying on semantical rules that Quine is criticizing, but on philosophical grounds rather than mathematical grounds. The fact that Quine's famous criticism of Carnap can be seen as an echo of MacLean's is perhaps not just a coincidence, or a case of both men recognizing the same basic problem. For Quine and MacLean were acquainted with each other during the 1940s when MacLean was at Harvard, and they even sailed together on occasion. It's hard to imagine MacLean not mentioning his critique of Carnap to Quine under such circumstances, given that Quine was at the time well known as a budding logician and avid student of Carnap's works. I think I'm up to section 4 now, if my numbering is correct. Carnap's semantics. After effectively demolishing the logical syntax in his review, MacLean goes on to propose that the basic concepts of general syntax, like the logical symbols of a language, be treated, he says, quote, in a more postulational manner, although he does not suggest any specifics. Such an axiomatic approach to logical truth would indeed have been good Göttingen-style mathematical practice, following in the abstract axiomatic tradition of the Hilbert school, with which he was well acquainted. But it was incompatible with the modified logicist program that Carnap had adopted after 1931, which in some ways was essentially still Fregean, in the spirit of Gottlieb Frege, Carnap's teacher. Perhaps MacLean had in mind something like the position developed by Bernays in the paper Philosophy of Mathematics and Hilbert's Proof Theory from 1930. In this paper, Bernays argues that logic is essentially mathematical and not the other way around, and that an abstract axiomatic approach to logic is required for a proper understanding of its essentially formal mathematical character. This Hilbertian position, in the spirit of David Hilbert, with respect to logic, is in stark contrast with Carnap's still quasi-Phrygian view, according to which mathematics derives its truth from the same source as logic, namely a codification of the rules for drawing inferences, abstracted of all empirical content in a given formal language. According to Carnap's principle of tolerance, these rules themselves could be stipulated by the conventions of a particular language, but the mathematical aspect of the language was then still essentially logical, i.e., formal linguistic. This essential distinction to be drawn for Carnap was not between mathematics and logic, but between the formal syntactical, encompassing both mathematics and logic, and the contentful empirical, relating to meaning and truth. But soon after reading Tarski's famous paper on truth in 1936, Carnap concluded that Tarski had offered a fitting replacement defined by precise rules for the common sense concepts of meaning and truth. According to his own doctrine of tolerance, these could therefore be readmitted provided we agreed to let our use of them be guided by Tarski's precise definitions. So, Carnap now went on to study not only the formal syntax of scientific languages, but also its semantics, the relations between sentences and what they refer to. It may be that Carnap really was led to accept Tarski's semantics by adherence to his principle of tolerance, as he suggests, but he was probably also moved by the need to find a satisfactory general characterization of analyticity, one not subject to MacLean's objection. In either case, finding such a characterization soon became the focus of his research. Carnap's semantic definition of logical truth encompassed languages of a very general kind, ones that also contain non-logical and non-mathematical terms, and this suited his purpose of treating logic and mathematics as part of the language of science. But he was therefore also faced once again with the problem he had confronted unsuccessfully, as MacLean had shown, of distinguishing logical truth in particular from general semantic truth. In Tarski's theory of truth at the time, there was no inherent difference between mathematical and empirical truth. The truth predicate in Tarski's early theory applies equally to all sentences without distinguishing a special class of logical ones. So what Carnap thus lacked still was a way to distinguish the analytic or logical truths from the empirical, or as he later called them, descriptive ones, essentially the role of the notion of tautology in early logical empiricism. This distinction, he thought, was not just a philosophical necessity, but had a fundamental practical importance for science as well. In a passage often cited by Carnap, Einstein had said, quoting from Einstein now, "Insofar as the sentences of mathematics refer to reality, they are not certain. And insofar as they are certain, they do not refer to reality. I place such a high value on this conception of geometry because without it the discovery of the theory of relativity would have been impossible for me." End of the quote. In his various attempts to give a precise formulation to this distinction after 1940, Carnap seems to have been guided by at least two further pragmatic constraints representing a sort of design preference for suitable languages of science. One was that the analytic truths should capture at least customary logical reasoning. While it was certainly permissible to consider languages with different consequence relations, the ones Carnap in fact considered were usually extensions of classical predicate logic. The second, less explicit constraint was that the logical and mathematical sentences should be determinate in the sense that every sentence should be either analytic or contradictory. We saw this before. This constraint of determinacy may have derived from Carnap's assumption of classical logic, but it was also related to his intent to portray mathematics as contentless, having no objects of its own and requiring no non-trivial assumptions. If he ignored MacLean's advice to take a more postulational approach, he nonetheless did take the point about the difficulty of distinguishing the logical part of the language, for he soon embarked on his ambitious series of books, Studies in Semantics. And the first volume to be written, entitled Formalization of Logic in 1943, was devoted to precisely MacLean's problem of giving a distinction between logical and descriptive symbols. The investigation of the semantic notion of truth itself was conducted in the subsequent book, Introduction to Semantics. A different approach, using modal logic, was finally pursued in Meaning and Necessity in 1947. In the appendix to the book Introduction to Semantics, in which the modifications required to the syntax are indicated, Carnap writes, quote, "The most important change concerns the distinction between logical and descriptive signs," so exactly MacLean's problem, "and the related distinction between logical and factual truth. It seems to me at present that these distinctions have to be made primarily in semantics, not in syntax." Well, because the distinction in syntax hadn't worked. Unfortunately, however, the treatment given in the body of the book to this most important issue is also the most unsatisfactory. The detailed treatment presented in the Introduction to Semantics is much like Tarski's early theory, in which a semantic system consists of a given formal language together with a fixed interpretation in a meta-language determining which formal sentences are true and which ones are false. So it's essentially the method on this slide that I just showed you for analyticity, but now what's being defined is not analytic by recursion, but rather truth in a given interpretation, truth in a fixed interpretation. This method provides a characterization of the true sentences in the language with respect to that interpretation, but not the logically true ones. Carnap at times suggests that the logically true sentences are to be those that are true solely in virtue of the semantic rules for the logical constants, without regard to the actual truth values of the atomic formulas. But he doesn't even try to develop this vague notion into a formal criterion. Strangely, the crucial problem of distinguishing the logically true sentences from those that are merely true is simply never satisfactorily resolved, as Carnap himself frequently admits. So here's quoting from the Introduction to Semantics near the very end. Quote, "The distinction between logical and descriptive signs and the distinction between logical and factual truth belong to the most important problems of logical analysis. Our previous discussion has shown the difficulties connected with the problem of a general formulation of these distinctions. This problem is very much in need of further investigation." And in another passage he calls it, quote, "one of the most important problems in the foundations of logic and perhaps in the whole of theoretical philosophy," unquote. And even Tarski himself was, at the time, quite skeptical about the possibility of distinguishing logical from factual truth in the context of his own semantic theory. For Carnap, there are several distinct but related problems here that would all need to be solved in order to get a workable definition of analyticity or logical truth. First, despite the efforts in the formalization of logic, there remains MacLean's problem of capturing the distinction between the logical and the descriptive symbols in a general way that applies across language. Quoting from Carnap, "So far we've discussed the distinction between logical and descriptive expressions only in the form in which it appears when we have to do with a particular semantic system. The problem is much more difficult in the form it takes in general semantics. Here the question whether and how logical and descriptive can be defined on the basis of other semantical terms is not yet known. A satisfactory solution is not yet known." That's one problem. Secondly, there's the problem of how to unpack the all-important notion that the truth of a sentence follows from the semantic rules alone. Carnap's idea in the syntax had been to identify the logical truths with the semantic truths consisting entirely of logical symbols, assuming the latter could be determined. But in the present context, in which all terms are interpreted and some terms are descriptive, this proves to be far too narrow. For just consider the difference between just a simple example. I mean, for an arbitrary sentence here, f of a, on the one hand, may be true in the fixed interpretation, but also f of a or not f of a is going to be true in every interpretation. This one is true as a result of the specific interpretation. This one is true regardless of the details of the specific interpretation. And so Carnap needs a way of distinguishing between this kind of truth and this kind of truth. Now, Carnap wants to say that the truth of the second kind holds independently of the interpretation of the non-logical constants f and a occurring in it. That is, in the second case, it will still remain true if a is replaced by b or if f by g and so on, but it would of course fail to remain true if the symbol wedge for conjunction is replaced by a hat if the symbol wedge for disjunction is replaced by a hat for conjunction. So the sentences that are true in virtue of the semantic rules alone could be described as those such that all substitutions for the non-logical symbols remain true. But this again requires the distinction between logical and descriptive symbols, which is exactly what MacLean showed to be defective. Third, under the semantic approach, it becomes necessary for Carnap to somehow demonstrate that logical truth does not depend on or imply factual truth, that it's truly contentless. This was to have been ensured in the syntax approach by the condition of determinacy. But with the introduction of mixed logical and empirical concepts and propositions, there's a real danger that the two might become entangled. One solution would be to again ensure that every purely logical sentence is semantically determinate, either uniformly true or uniformly false, under all permissible substitutions, as we talked about here, for then its content, its consequence class, would in any case be trivial. But this last proposal raises yet a final problem. Even given MacLean's distinction between logical and descriptive symbols, in order to identify the permissible substitutions, there's still a more fundamental problem with the general approach in Carnap's early semantical works. In order to determine what Carnap then called L-truth, what we would call logical validity, it generally does not suffice simply to substitute different constant symbols and check the result in a single interpretation as Carnap does. Instead, the idea that the truth of a logically true sentence is independent of the interpretation of its non-logical symbols, which is clearly Carnap's intent here, has been captured in logic since the 1950s by considering the range of all possible interpretations of those symbols, not just the ones already named by another symbol in the language. Again, over all possible domains of quantification. Only something like this will suffice to show that every semantic consequence of an L-truth is again an L-truth, for instance, ensuring that logical truth is empirically empty. So, in model theoretic terms of modern logic, what's required is the difference between truth in a particular model and truth in all models. Remarkable as it may seem, this idea of rigorously defining logical truth for a given language by considering the range of all its possible semantic interpretations was somehow absent from logic in the 1940s. Although this conception is now taken for granted and it seems obvious enough to us, it is simply not present in Tarski's famous paper on truth in 1936, nor in his other works until around 1952. It's also absent from Carnap's early semantic works. His systems invariably consist of a language with a single fixed interpretation. Perhaps the reason Carnap did not arrive at the notion of logical validity is that it assumes the logical symbols as simply given by postulation for the purpose of varying the interpretations, and that was something Carnap refused to do on philosophical grounds. That would be especially ironic, since one possible solution to MacLean's problem of distinguishing the logical constants also depends on variation of just this same sort, and is in fact related to Carnap's idea of characterizing the logical symbols through determinacy. The intuition behind that property was picked up and investigated by Tarski and proposed as a characterization of the logical part of the language more generally. The logical operations on any domain of variables have the special property that they are invariant under all permutations of the domain, regardless of its size. The analogy that Tarski had in mind, of course, was Klein's Erlanger program of the late 19th century, in which geometries are characterized in terms of the features that remain invariant under different groups of linear transformations. It's clear that the idea fits well with Carnap's idea of characterizing logical symbols by determinacy, and like the concept of logical validity, it once again represents a completion of Carnap's work by applying more sophisticated mathematical tools. In sum, then, Carnap's idea of characterizing logical truth using semantics was by no means a false start, but Carnap himself lost interest in its development because it did not fulfill the philosophical hopes he had pinned on it. From the viewpoint of his quest for a definition of analyticity, there is indeed a basic problem with this approach to logical truth, even if understood in the present-day sense of logical validity, true under all interpretations of the non-logical terms. The characterization is still dependent on the choice of methods used in the semantic meta-language, the range of interpretations presumed. This is obvious at the level of higher-order languages, for which, for example, the validity of the axiom of choice depends on whether that law is assumed in the meta-language that you're using to give the semantics. Even in the first-order case, the case of first-order logical validity, the same obtains for the law of excluded middle. Thus, the element of arbitrariness in the syntax definition of analyticity, which originally gave rise to the principle of tolerance, remains under the semantic approach. This meta-linguistic relativity is an inherent feature of the semantic approach to logical truth and was not going to be remedied even by resolving all of the problems in Carnap's studies in semantics. Section 5, Logic in the Stone Age. Carnap abandoned his studies in semantics just as the Stone Age was dawning in Chicago, and MacLean returned from Harvard along with a new stable of bright lights recruited by Marshall Stone from around the world to build up a leading mathematics department. MacLean was by then firmly established in algebra and topology, having already done his famous work with Eilenberg on Eilenberg-MacLean spaces, cohomology of groups, and published the first papers in category theory. There was, of course, no logic in Stone's Chicago, nor for many years thereafter, but for reasons that I cannot entirely reconstruct, maybe someone here can help me, around 1952, a small group of Chicago graduate students, including Anil Narode, Bill Howard, Ray Smulyan, and Stanley Tenenbaum, began taking an interest in logic and looking for someone to teach it to them. At some point, John Myhill was also there, but I don't know when. One of these students, Narode, went across the quads to philosophy, where Carnap was, in Chicago at the same time, and asked Carnap for supervision. Carnap told him to go back to MacLean instead, who he said had studied logic with Bernays, advising him moreover that the future of logic is in mathematics. As Narode reports it, quoting now from Narode, Saunders did his logic dissertation under Bernays, but immediately left logic for algebra and topology. His knowledge of Bernays' class theory meant that he knew exactly how to formalize category theory when he and Eilenberg developed the subject. The concept they wanted to capture at the time was natural equivalence, needed to explain the relationship between the many homotopy and, I promised not to use the word homology, didn't I, that had been developed. In about 1952, there were several students in mathematics at Chicago interested in logic, Narode, Howard, Smulyan, and Tenenbaum. They persuaded Saunders to sponsor an informal logic seminar, which he attended and in which he delivered polished lectures on the latest papers. The first two, and then Michael Morley, took their PhDs with him, respectively in recursion theory, proof theory, and model theory. He was a very broad mathematician. Ray Smulyan went to Princeton to get a degree with Church, and Stanley Tenenbaum never did a PhD but contributed to independence proofs in set theory. So this was a very successful seminar. Solovay did a topology thesis with Saunders but jumped into independence proofs in set theory as soon as Cohen gave his Princeton lecture. Throughout Saunders' later career, he tried to get logicians to develop mathematics in category theory because he thought this would give a better foundation for set theory. As Bill Howard recalls, quoting from Howard, in the spring of 1954, through conversations with Smulyan, Tenenbaum, and the others, I had arrived at a number of ideas about a constructive foundation for mathematics, but I saw no possibility that the mathematics department in Chicago would accept a dissertation in this area, mathematical logic. Then one day, Nerode told me that MacLean had agreed to allow us to write our dissertations in logic. Howard, what made you think of MacLean? Nerode, I found out that he wrote his own PhD dissertation in logic. So by that time, MacLean was so firmly in logic and related fields that his students didn't even suspect an interest in logic. So firmly established in algebra that his students didn't even suspect an interest in logic. To my knowledge, he had no significant further interaction with Carnap, either at Harvard in the 40s or back in Chicago in the 50s, beyond lifting the term functor from the logical syntax. During the Stone Age of the 50s, MacLean himself did no further research in logic proper, apart from supervising the 4 dissertations mentioned by the students, but he did stay involved in other ways. For instance, as a member of the National Academy of Science, he nominated Gödel for a National Medal of Science, arguing that he deserved it as the greatest logician since Aristotle. When the medal was actually awarded at the White House and Gödel was too ill to accept it in person, MacLean accepted it for him from President Ford and delivered it personally to Gödel in Princeton. Upon receiving it, so the story goes, Gödel put it on and complained that it was heavy. You don't have to wear it, was MacLean's reply. Last section 6, a late return to logic. A new chapter in MacLean's involvement with logic was opened in the early 60s by Leviere's ideas on applying category theory to study logic algebraically and relate it to other fields, such as algebraic geometry. Saunders took a keen interest in this work, and once he was convinced of its promise, he became a great supporter of it. When topos theory arrived on the scene a few years later, he was back into logic with both feet, supervising research, organizing seminars, writing expositions, and lecturing on the subject around the world. In the course of lecturing on toposes at Cambridge, he sparked and then tended the fire of Peter Johnstone's dissertation. At the time, in the early 70s, MacLean himself had been preparing to write a book on topos theory, but he put his own project aside when Johnstone declared his intention to do the same. He even provided Johnstone with a few chapter drafts. MacLean continued into his 80s to pursue the development of topos theory with burning interest, supervising research, and eventually writing a book in toposes after all, with Ecole Moerdijk, which has become the standard textbook in the field. Perhaps this is a good point to briefly digress, if you'll permit one more Carnapian digression, to point out that the semantic problems with which Carnap had grappled in the 1940s have in the meantime been solved, some in the immediate wake of Carnap's own work, and some only recently using the logical methods developed by MacLean, Leviere, and others. The modern conception of logical validity as truth in all models is essentially the notion of analyticity that Carnap himself later accepted. Similarly, Carnap's treatment of modal logic was later subsumed by Kripke's account of what we know as Kripke semantics. As good as these solutions were as a starting point, they do not fully address the issues with which Carnap struggled, the basic problems of distinguishing logical from descriptive truth and showing the former to be empirically empty, as well as what we've called the problem of metalinguistic relativity, are not so much addressed in these schemes as they are taken as given by postulation. These issues are resolved, however, by certain modern-day extensions of those solutions, as I will now try very briefly to indicate. The essential ingredient that was apparently missing from Carnap's early attempts in both general semantics and modal logic was, of course, the idea of allowing the interpretations for a given fixed language to vary while the language itself is held fixed. The modern semantic notion of logical validity, as well as Kripke semantics for modal logic, both employ this device in an essential way. This variational approach is taken even further in the topos theoretic treatment, employing MacLean's theory of categories and functors. This treatment is a natural generalization of the earlier approach, which not only subsumes the familiar notions of logical validity and modal necessity, but also succeeds finally in distinguishing the logical constants from the descriptive vocabulary through invariance, as was proposed by Tarski. The latter was only shown recently, 1998, in a paper by Karsten Butz and Ike Moerdijk, but more could be done in this direction. Moreover, the modern functorial approach also provides an understanding of the incompleteness phenomenon which had so vexed Carnap's attempts in terms of variation versus constantly. Very briefly, provable is equivalent to true in all variable models, while true but unprovable is equivalent to true in the constant models and sets only. This solves the problem of metalinguistic relativity as well, since the resulting notion of logical truth in its most basic form simply agrees with provability and so is essentially independent of the choice of a meta-language. The modern functorial approach thus solves most of Carnap's problems. It's incompatible, however, with one of his basic constraints, the determinateness of all logical and mathematical sentences. It turns out that some features of the mathematical universe, such as the cardinality of the continuum, must also vary, thus remaining logically indeterminate. This can be a useful and powerful device, and one which is apparently not at odds with the purposes of science. Recall that it was the contentlessness of logic and mathematics that was presumably motivating Carnap's constraint of determinacy. For the classical law of excluded middle implies determinateness of logic and mathematics from empirical facts. But from a modern perspective, this desired emptiness of empirical content can be achieved in another way, namely through an understanding of mathematics as the study of abstract structures and their structural properties. In its recent formulations by MacLean and some of his followers, this position is a modern descendant of Hilbert's axiomatic program, using the mathematical structuralism of Bourbaki. In other words, modern structuralism is a realization of the more postulational approach that MacLean suggested to Carnap back in the 1930s. According to this view, abstract, axiomatic logic and mathematics provide the pure form of scientific theories, the content of which is supplied empirically. Thus, for Carnap in the 1930s and 40s, some version of Frege's logicism had still seemed like the most natural approach to realize his goals for an empiricist understanding of logic and mathematics. But today, Hilbertian structuralism, as formulated by MacLean from the viewpoint of category theory, seems like a much more promising alternative. In this way, MacLean's late book, Mathematics, Form and Function, may represent the fruition of the philosophical aims that he mentioned in the letter to his mother from Göttingen in connection with his interest in transferring to Vienna. And his late return to logic through the work of Leverrier and then in topos theory clearly demonstrates the inaccuracy of the general impression expressed by Nerode that MacLean left logic after his dissertation. Instead, as I've argued, MacLean clearly maintained an interest in the field throughout his life and later even returned to it, making and supporting essential contributions using the categorical methods that he himself had developed. Moreover, I think an argument can also be made that MacLean's greatest work, the development of category theory at the height of his powers, should itself properly be regarded as a contribution to logic, and indeed one of a deeper and more lasting kind than would have been, say, some theorems in recursion theory. As a conceptual tool of the highest caliber, on a par with modern formal logic itself, category theory has proven its value in articulating the structure of arguments, operations, and constructions throughout mathematics in ways that more traditional areas of logic cannot even approach. And in fact, this sort of conceptual organization matches far better MacLean's own declared ideal of the proper role of logic, which, as he wrote in his dissertation, was not as a separate and highly specialized field in itself, but rather as providing the leading ideas for the purpose of studying, quote, the structure of the elements of mathematics, in order to, quote, strengthen the connection between mathematical logic and mathematics. Thanks for your interest.
Je vais lancer la discussion.
Yeah, Alberto.
Thank you. Steve, would you precise the point you suggested concerning the fact that MacLean anticipated, in a sense, Quine in criticizing the distinction between analytic and synthetic?
Yeah.
So this is the point, because well, there are many issues involved in that critique. So,
Right.
and another remark, more than a question, is that I mean, if we take into account the way mathematics form and function is constructed. It's true. I mean, I don't want to say that that architecture is such that we can say that structuralism is incompatible with it. I don't want to say such a claim,
Right.
but I wish to stress that it is compatible also with another view. That is, that he is preoccupied with giving substantial meaning to basic mathematical notions, relating these notions to activities such as counting, measuring, collecting, dividing, and so on. And these activities are embedded in actions performable in the physical world. So in a sense, I mean, this is a way that could be very palatable to a phenomenological view of mathematics.
Thanks. I'll start with the second point. Definitely, I appreciate the difficulties involved in structuralism as such, as a position for understanding the nature of mathematics, and principally the difficulty that you're pointing out of connecting the theory of mathematics with, at its very most basic level, the practice of counting and measuring and so on. So this is the essential problem with structuralism. And so I would definitely not want to tie the understanding of category theory too tightly to structuralism, because category theory is much more solid than structuralism. It's more like structuralism achieves its support by hanging it onto category theory. Yeah. So I agree with you on that point. As to the first point, the question of Quine's famous critique of Carnap, which is generally considered to be his great contribution to contemporary philosophy, is the observation that Carnap has not succeeded in distinguishing analytic from synthetic. There I maintain that MacLean simply preceded him in calling attention to the fact that Carnap had not done it, and in emphasizing the importance of the fact for Carnap's program. MacLean just had him by 12 years. And moreover, as I tried to suggest discreetly, I think Quine even got it from MacLean, because they were pals at Harvard, they went sailing together and so on. So, and MacLean was certainly Quine's elder by about 10 years. Now, that's not to say that the substance of Quine's specific analysis of Carnap's attempt derives from MacLean. MacLean's argument is a different one. It's a mathematical critique of the specific definition in the syntax. By the time Quine got around to criticizing Carnap, Carnap had proposed a different approach, a different fix in response to MacLean's critique. So then when Quine went to look at what Carnap was doing to check whether MacLean's objection still obtained, he found different reasons for criticizing Carnap. So Quine's argument is a different one than Saunders was, but the point of the argument is the same. So that's all I want to say. Jean, here in the front.
after this beautiful talk, I would like to make just small remarks
Please.
about the interest of MacLean towards logic much later than what he's supposed to.
Yes.
And in particular, you mentioned Carnap, you mentioned Quine, but he was interested also in Gensen, in cut elimination theorems, which he even used for coherence.
Ah, yeah, that's right. Yeah, yeah.
So he knew
Yeah,
that,
yeah, that's
and
good,
he
yeah.
knew the use of it.
Yeah, that's absolute.
And it's a beautiful piece of logic,
Mhm.
but MacLean was aware of it and used it in a nice manner.
Oh, thank you. That is priceless. That observation is priceless. Thanks for that. Because he was definitely aware of Gensen's work. They had been students together in Göttingen, and absolutely it was an inspiration for his work in proving coherence theorems. Thanks for that.
Just an anecdote to add at this point. Saunders did not write a lot of marginal notes to my knowledge, but the most informative marginal note he has complains of Krul at one point in his Idealtheorie, invoking Zorn's lemma to prove that there's a maximal subset with a certain property, because there is a unique one, and which shows that you didn't need Zorn's lemma. I mean, in the particular case, he shows that you didn't need Zorn's lemma. So that point you were making about his criticism of Carnap, and he knows the difference between, sure, there are maximal ones, but
Yeah.
yes. Well, his sensitivity to the point is attested in the most informative marginal note I know him to have written. Marginal note, yes. Note in the margin of a book, yes.
Yes, this actually anticipates a bit on Jean Benabou's question. Do you know by any chance what MacLean's position was about like recent developments in logic? That, for example, in linear logic, where proof theory becomes graphical, and like the cut elimination really becomes like graphical construction. So.
For coherence,
Yeah, that's what it is. But now, like, if you take Girard's linear logic, you've got proof nets. So the proof itself, in a linear logic, like the proof itself becomes like graphical, and cut elimination is just like graphical reconstructions. Did MacLean has an opinion on that? These things?
He was aware also of the work of Lambeck and others, which described proof theory, not exactly proof theory, but the equivalence of proofs, classes of equivalence of proofs, as the way to construct free, say, structures of two dimensions. Say free monoidal categories, etc., etc., free closed categories can be constructed as just equivalence classes of proofs in a given language. And again, the influence of Lovier, which of course you mentioned, goes maybe far beyond what we may think, because category theory is exactly as at the junction between logic and proof theory. And in particular for Lovier, already in his dissertations, etc., an algebraic theory is a category, is nothing but a category with finite products. And then it became true for other kinds of theories. Theories now tend to be identified with categories which have some specific properties.
Okay, merci.
Thank you.